All right, this is the practice chapter 10 test, and as always, I am the amazing Mr. Jansen. So away we go. If we take a look at these first two, it says to solve each, and notice it doesn't specify how it wants us to solve each of these. So really, I could use logarithms to solve this since these are exponential functions. But the easiest way to solve these is to see if we can get the same base on each side. And in these, we can. In other words, right here, the 4 I can rewrite as 2 to the second power. And then what happens is I multiply the exponents. So instead of a 4, I write it as 2 to the second. Over here, 1 over 8 I can rewrite as 2 to the negative third power. And again, with the fractions, just look at the denominator. 2 to the third power is what gives me the 8. So to get a 1 over 8, I just do 2 to the negative third. Okay, that's what negative exponents do. So now each side is rewritten. I rewrote each side so that they have the same base. And when we have the same base on each side, it means the exponents are equal to one another. So that means the 2 times the x plus 1 equals the negative 3. I'm going to distribute. I'm going to go ahead and distribute this guy a while. So that's 2x plus 2 equals the negative 3. And then I solve for x, so I subtract the 2 from each side. So I find out that 2x equals a negative 5. And then I got to divide each side by the 2. And you can either write this as a negative 5 halves, or since some folks might use their logarithms, you could have it written as x equals a negative 2.5 as well. I'll accept either one. Okay? For the next one, I want to do the same thing because I can rewrite these so that they have the same base, so I might as well. 27 is the same thing as 3 to the third power. Again, I multiply the exponents. 9 is the same thing as 3 to the second power, so I multiply the exponents. And now that I have the same base, it means the exponents are equal. I'm going to go ahead and distribute in this first step. So that's 6x plus a 24 equals a 4x minus 8. I've got to get my x values on the same side, so I'm going to subtract the 4x from each side. So I get 2x plus 24 equals the negative 8. Now I subtract the 24 from each side. So I get 2x equals a negative 32. And then divide each side by 2. So I find out here that x equals a negative 16. And that's it. All right, piece of cake. All right, so when you can rewrite them so they have the same base, that's the way you should do it because it's the easiest method. If I look at the next one, it says to use the properties of logarithms to rewrite this expression as one logarithm. So right now, I've got 3 separate logarithms. And I can't start combining them. I've kind of got to follow order of operations here. I can't combine these into one logarithm until I have just logarithms for each one. So the first thing I need to take care of is this 3 that's out front. Remember, multiplying by a 3 on the outside of a logarithm, I can rewrite that as an exponent. So this is going to be log base 2 of x plus, this becomes log base 2 of y to the third. See, I take that multiplication and I rewrite it as an exponent inside the logarithm. The next thing I'm going to do is I've got addition of 2 separate logarithms, which I can rewrite as one logarithm of the 2 things being multiplied. So I can rewrite this as one logarithm of x times y to the third. Okay? Minus log base 2 of 5. And now I have 2 logarithms being subtracted, which I can rewrite as one logarithm of the 2 things being divided. So I'm going to do y x to the third over 5. And that's it. That's my answer. Log base 2. Let me rewrite it over here so you can see it clearly. xy to the third divided by 5. Okay, that's my final answer. It's rewritten all as one logarithm. Okay, so I've condensed it. In number 4, we're doing the very opposite of that. We want to expand this into multiple logarithms. So before I had multiple logarithms, I rewrote it as one logarithm. Now I have one logarithm, and I'm going to expand it out. So first things first, I've got the natural log of 3x divided by y squared. One logarithm of 2 things being divided, I can rewrite as 2 separate logarithms of the natural log of 3x minus the natural log of y squared. Okay, so I can split it up that way. Division of one logarithm, I can rewrite as 2 logarithms being subtracted. And now here, I've got 2 things being multiplied. It's 3 times x, which I can rewrite as 2 logarithms of those 2 things being added. So it's the natural log of 3 plus the natural log of x minus. Over here, I'm going to go ahead and do this rule. I can take this exponent and I can bring it out front and turn it into multiplication. So it becomes 2 natural log of y. And that's it. That's all I can do. That is expanded as far as it can be expanded. So that's my final answer. Okay, that's it. All right, so using our properties of logarithms in two different ways, using it to condense and using it to expand. The next one is super simple. This one we're going to use our change of base formula. So I've got log base 7 of 98, and I wrote a 2, but I said a 7, so here let me try again. 7 of 98. And I can rewrite this using one of the logarithms that I know, either in the natural log or the common log. Right? So option number 1, you do the natural log of 98, the natural log of what was already in the logarithm, over the natural log of the old base, which is the natural log of 7. All right? Or you could use the common log. You could do common log of 98 over the common log of 7, whichever one you prefer there. And just to show you how to plug this into the calculator, I've got my calculator ready to go here. So the first one, natural log of 98. And again, make sure you close that parenthesis divided by the natural log of 7. Again, close the parenthesis. You get, see, to 3 decimal places, 2.356. And just to show you, if I use the common log of 98 divided by the common log of 7, it gives me the same answer. Okay, so either one, that's our change of base formula. Again, the change of base formula says we can use whatever base we want. Right, so use either common log or the natural log. All right, and that's it for that one. Moving right along. If I take a look at this guy, I want to solve this. So the first thing I want to do is I want to kind of condense this. I'm going to use my properties of logarithm to rewrite this as one logarithm. I can't start undoing the logs until I've kind of simplified them as far as they can be simplified. So right now I have 2 logarithms of the same base being added, which means I can rewrite them as one logarithm of the 2 things being multiplied. So I can do x times the x plus 6. So you rewrite them as one logarithm. And if you wanted to go ahead and do this distribution all in one step, that's fine. So if you did write to log base 3 of x squared plus 6x, that is perfectly acceptable. And now I have log base 3 to undo logarithms. I use exponential functions. Just like to undo exponential functions, I do logarithms. So I'm going to do 3 raised to the power of each side. So it's like each side of my equation becomes the exponent, and I use 3 as the base. Because what happens over here, log base 3 and 3 raised to a power cancel each other out. So I'm just left with the x squared plus 6x. Over here, I literally have 3 to the 3rd power, which is 27. And now I'm going to solve this by factoring. Take it off to the side here. So I'm going to subtract the 27 from each side to get this whole thing set equal to 0. So I've got x squared plus 6x minus 27 equals 0. I build a bridge and solve by factoring. I build a bridge, that's a negative 27. 2 numbers that multiply together to give me a negative 27, but add together to give me the positive 6 is going to be a positive 9 and a negative 3. So this factors into x plus 9 and x minus 3. And then I set each factor equal to 0, so find out that x equals a negative 9 and x equals a positive 3. And remember, with logarithms, we have some special scenarios here. We cannot plug a negative into a logarithm. It just doesn't work, which means this is an extraneous solution. I can cross that fella out. So the only answer here is x equals 3. Okay? For this next one, again, I want to start off the same way. I've got to condense this to one logarithm. So right now I have 2 logarithms of the same base being subtracted. I can rewrite it as one logarithm of the 2 things being divided. So that's going to be an x squared minus 4 over the x minus 2. Over here I've got log base 5 of 8. And now to undo log base 5, I can do 5 raised to the power of each side. And what happens, log base 5 and 5 cancel, log base 5 and 5 cancel. So I'm left with x squared minus 4 over the x minus 2 equals 8. And now from here, there's a couple ways I can solve this. Here's the easiest way. If you notice this, x squared minus 4 is a different squares. That factors into x plus 2, x minus 2. And what happens with the x minus 2s is they cancel out. So essentially, I'm left with x plus 2 equals 8. I subtract the 2 from each side, and I find out that x equals 6. Okay? And it almost appears that I'm missing a solution here because the other way to solve this, let me show it to you the other way real quickly. you could multiply each side, give myself some space here, by the x minus 2. This is the way a lot of folks did it. Here the x minus 2's cancel, so you've got x squared minus 4 equals. Here you distribute and you get 8x minus 16. And then you have to subtract the 8x and the 16 over, so you get x squared minus 8x. I've got to add the 16 over, so that's going to be a plus 12 equals 0. And then if you solve this by factoring, you build a bridge here, and you get the positive 12. The two magic numbers here are going to be a negative 6 and a negative 2. So this factors into x minus 6 and an x minus 2. And when you set each of those equal to 0, you get x equals 6, but you also get x equals 2. And it appears at first glance that both of those work, but when you think about it, if you plug a 2 in here, you're going to get a 0 in the parentheses. Same thing here, you get a 0 in the parentheses. And the logarithm of 0 is always 1, so essentially what you get here is 1 minus 1, which is 0, which does not equal the log base 5 of 8. Okay, so you always have to check these and plug them back in. Even though x equals 2 is positive, it's still an extraneous solution because it doesn't work. All right, so the best way to do it is to find out about the factoring and cancel out that x minus 2 first. Okay, so keep that in mind. Be aware of those extraneous solutions. For the next one, it says to solve each and round to 4 decimal places. And right away, since it's telling me to round to 4 decimal places, I'm not going to be able to rewrite these so they have common basis. All right, there's no number that I can do raised to a power that gives me 7 that also gives me 21. All right, so since I can't get common bases, I have to use logarithms to solve these. For this one, since there's only one exponential part and it's already by itself, I would use log base 7 to solve this one. And if I take log base 7 on one side, I have to take log base 7 of the other side. So now I've taken log base 7 of each side, and what happens is log base 7 and the 7 cancel over here, so I'm just left with x minus 5. Over here, log base 7 of 21, I have to use my change of base formula. That's the natural log of 21 over the natural log of 7. And to finish solving for x, I just have to add the 5 to each side. Okay, so when I do that, I get x equals the natural log of 21 over the natural log of 7 plus the 5. And this is now just a job for my calculator. So again, be careful as you plug this in. Let me plug it into my calculator. I've got the natural log of 21 divided by the natural log of 7. And if it makes you feel more comfortable, I like to take care of order of operations myself. I'm going to hit enter. So now I've done the division. Now I'm going to add the 5. All right, your calculator's smart enough. I could have just done the plus 5, but it's nice to take order of operations out of the calculator's hands. You'll make less mistakes. So you get 6.5646, okay, to 4 decimal places. And that's it.